Hello everyone, my name is Jun Fan, and I'm very happy to be here in CBP 2025 workshop. So the title of my presentation is Branch Prediction via Load Value Prediction, the case of ball predictor. So first I will introduce the motivation of the ball predictor. Then I will introduce the detailed predictor operation, and at the last the performance results. So I started to design this ball predictor by analyzing traces of MPKI larger than 10 by 64 kilobyte TJSCL. There are 8 traces of MPKI larger than 10, and I list them here. So next I will show you the analysis of 4 of them to motivate the ball predictor. And each of the analysis is with their most mispredicted branches. The first one is int 21. So the branch is dependent on 3 loads. The address of the first load is constant stride. The address of the second load is pointer chasing dependent on the first load. The base is the first load data, and the offset is a constant. The address of the third load is fixed, and it can be treated as a special case of constant stride with stride equals to 0. The load data of the second and third load are compared with each other to set the flag register and to determine the branch direction. The second trace is int 1. The feeding load is also constant stride, and it works between 2 boundaries. The load data is compared with integer 0 implicitly to determine the branch direction. The third trace is FE8. The feeding load address is also constant stride, and the load data is compared with floating point 0 to determine the branch direction. The last trace is FE13. Unlike the previous 3 traces, the feeding load address is correlated with global branch path history, and the load data are compared with each other to set the flag register and determine the branch direction. So to summary, the ball predictor is a pre-computation engine computed on Branch-ALU-Load-Load dependence chain. So I show you a diagram of the chain. And the overall predictor is combined by 64 kilobyte TJSCL and 128 kilobyte ball. The ball targets at load data dependent branch. It acts as follows. First, it predicts the load address by these 3 patterns, and then predict the load value by using the predict address to access the data cache. Then predict the flag register value by using the predict load value. They are compared with each other or compared with integer or floating point 0. And at the last, predict the branch on the predicted flag register value. So the second part is detailed predictor operation. When TJSCL mispredicted branch is commit, the dependence chain is built by tracking the register dependence. And to achieve this, there is a 96 entry commit queue to record committed instruction information such as PC, instruction type, source and destination register index. When the chain is built, the information is recorded in the conditional branch chain table, which is directly mapped and indexed by and tagged by branch PC. There is 1 branch node, 1 ALU node, and 4 load node in the conditional branch chain table. There are 2 more fields to be trained and used in prediction. First is the taken condition of the branch. Since NCCV flag has 16 combinations, so it's an array of 16 element size. The flag register is tracked at the commit stage, and the taken R64 will be increased if committed branch is taken, otherwise decreased. Then the ball can predict if the taken R64. This is the predicted flag register value is saturated, and will predict taken if it is positive, otherwise not taken. There is also a counter to select between ball prediction and page prediction. it is trained on the resolved branch, and it will increase if the ball hit predicted and the take mispredicted, and decrease if ball mispredicted. If the counter is larger than half of its max value, then choose the ball predictor, otherwise choose the take prediction. So for ALU node, the ALU PC is recorded, and the PC is also used to look up an ALU pattern table. If it is missed, then a new entry will be allocated. There is two fields to train and record the ALU type. To achieve the training, so architecture registers are tracked as commit. The calculated flag register using the tracked source register will be compared with the tracked one. If they are the same, then corresponding field can be set, and then the ALU type can be predicted by ALU PC. So for the load node, the load PC and the load piece information is recorded. They are also used to look up the load pattern table. There are three groups of fields to be trained and used in prediction. First one is for constant stride, and I will show you an example in the next slide. The second is for the point chasing offset. The offset is trained by calculating the load memory address. This is the committed load memory address. Subtract the source register to be tracked. And if the recorded one is same as the calculated one, the confidence will be increased. So the offset can be predicted using the load PC. The third group is to record the address predicted by branch path history. And in the board, the EV-TAGE is used from CBP1 by Andrew. And instead of predict the load value directly in the original EV-TAGE, the load address is predicted. So here I show you an example of stride training sequence. So the example I show you is constant stride with warp sequence. The address starting from 1, 2, 3, 4, 5, 6, 7, then warp again starting from 1. So it's almost like the hardware prefetch for constant stride. The difference of current commit address and the last commit address will be calculated as the current stride. If the current stride is different from the stride recorded and the confidence is 0, then we allocate a new stride pattern. And if the current stride is the same as constant stride, then we increase the confidence. When the warp happens, the current stride, the sign of the current stride is different from the constant stride. If the warp confidence is 0, then we allocate a new warp pattern. The warp address is recorded as the last address, which is in this example is the last address of the sequence. And the warp target address is recorded as the last commit address, which in this example is the first address in this sequence. And when the warp pattern happens again, the confidence will be increased. So when prediction, the address can be predicted by last committed address plus infinite count multiplied by constant stride. If the address, if the predicted address is larger than the warp address, for example, the predicted address is 8, then you need a warp start from 1 again to predict the actual address. So to predict the load value using the load address, there is a BB data cache to track load store values at commit. So it can contain 88 kilobyte data with 128 set 11 way. The cache line size is 64 bytes and with ALU replacement policy. To predict the load value, we can look up the BB data cache by using the predict load address. So there is also an end entry store resolve queue to track resolved but not committed stores. If it will invalidate the lookup from BB data cache if it is the same address in the store resolve queue. So to combine all the components, when the conditional branch PC hit a conditional branch chain table, the load PC is read to look up load pattern table and predict the load address. The load address is to access VB data cache and store resolve queue to predict the load data. The ALU-PC will also be read to determine the ALU type, and the load data is fed into ALU pattern table to predict the flag register value. The taken condition from chain table will determine the ball prediction, and finally the ball tage cell counter will choose between tage and ball prediction. Since there are multiple strike address patterns and they may have more than one patterns with high enough confidence, so they are marked by fixed priority. First is branch path history, second is constant warp pattern, third is fixed or increment pattern, and at last the point chasing pattern. The final part is the results. So the first one is the result of all workloads of the training traces. The combined tage and ball predictor achieved 3.542 MPKI and 148 cycle run pass PKI. Unfortunately, when compared with same area budget TGSCL, it cannot compete with it. It shows less 3% on MPKI and 2% less improvement on cycle run pass PKI. However, in the floating point workload, the combined tage and ball predictor shows more improvement than same area TGSCL. It shows 9% more improvement on MPKI and 3% improvement on cycle run pass PKI. So here the second result is only consider traces on MPKI larger than 10 by 64 kilobyte tage. The combined tage and ball shows more improvement than same area budget TGSCL. Shows 16% more improvement on MPKI and 7% more improvement on cycle run pass. And the ball predictor can achieve about 17% coverage on the misprediction by 64 kilobyte TGSCL, and the accuracy is about 97%. So here is all my presentation. Thank you.